Hello class, welcome to today's explainer. आज का topic ना is practically a scientific whodunit. I mean, for the longest time, we literally thought the atom was the absolute smallest thing in the universe, indivisible, unbreakable. But then scientists started finding these little clues. So chalo, let's dive into the true structure of an atom and trace this epic journey from classical physics straight into the wild world of quantum mechanics.
Here's our game plan for today, so dhyan se dekho. We're going to cover everything from the discovery of fundamental particles to the evolution of atomic models. Then, we'll tackle the math behind atomic numbers and isotopes. And finally, we'll get into the mind-blowing quantum mechanics of light and the photoelectric effect. Ready? Let's go.
All right, Chapter 1, the fundamental particles. Let's see how this discovery journey actually started.
So tell me, how did we first realize atoms weren't these solid, unbreakable blocks? Matlab, who broke the atom? Well, science is all about teamwork across time, right? It's an iterative process. Just look at this timeline. In 1830, Michael Faraday started playing around with electrical discharge in tubes. Decades pass, and in 1886, Goldstein discovers positive anode rays. Fast forward to 1897, J.J. Thomson figures out the charge-to-mass ratio. Then, Millikan literally drops some oil in 1909 to find the exact charge of an electron, and finally, 1932 में, James Chadwick finds that missing puzzle piece, the neutron. एक के बाद एक discoveries, pushing the boundary.
But how did this whole sequence really kick off? It all started with the cathode ray tube experiment. Picture this. Scientists passed electricity through these partially evacuated glass tubes. They noticed these mysterious rays traveling from the negative electrode, which is the cathode, all the way over to the positive anode. Now, since these rays were pulled towards the positive side, it was pretty obvious, wasn't it? These rays were made of negatively charged particles. Yes, electrons. They were hiding right there inside the atom the whole time.
So the absolutely crucial point here is knowing your basic cast of characters. ये table ना तुम्हारा ultimate cheat sheet है exam के लिए. We have the electron, symbol E- carrying a negative charge and an extremely tiny mass. Then the proton, P+, positive charge and much heavier. And finally, the neutron, N, which has zero charge, it's neutral, but a mass almost identical to the proton. पूरा का पूरा atom इन्हीं तीन चीजों से बनता है. ठीक है? Are we clear on the basics?
Awesome. Moving right along to Chapter 2, Evolution of Atomic Models. We know the parts, but who is sitting where? So we have our electrons, protons, and neutrons. But ये atom के अंदर actually fit कैसे होते हैं? Enter J.J. Thomson. He proposed what we call the plum pudding model, or, if you prefer a summer reference, think of it as the watermelon model. He basically imagined the atom as a solid sphere of positive charge, like the red, sweet part of a watermelon, and the negative electrons are just embedded inside it randomly, just like the black seeds. Overall, the positive and negative balance out so the atom remains neutral. Sounds simple, right? But hey, science never stops at the first good idea. Thomson's student, Ernest Rutherford, decides he wants to test this watermelon theory out. So he sets up the extremely famous alpha scattering experiment. He takes a super thin sheet of gold foil and bombards it with high-energy alpha particles, which are positively charged. He surrounds the whole thing with a fluorescent screen so he can literally see where the particles land. Now, based on Thomson's model, what he expected was that the heavy, fast alpha particles would just blast straight through that soft watermelon. But that is not what happened.
What actually happened completely blew their minds. Let's look at his exact observations. First off, 99% of the particles did pass straight through, completely undeflected. Okay, normal, as expected. Second, a very small fraction got deflected by small angles. Interesting. But the third point, oh man. About 1 in 20,000 alpha particles bounced straight back. Rutherford later said it was literally like firing a 15-inch artillery shell at a flimsy piece of tissue paper and having it bounce back to hit you in the face. No way, right?
To explain this completely wild observation, Rutherford had to totally change our view of reality. He realized the atom is almost entirely empty space. That is exactly why 99% of those particles just sailed right through. It turns out all the positive charge and almost all the mass are squeezed into a super tiny, incredibly dense center called the nucleus. To really visualize this scale, imagine a huge, massive cricket stadium. If the entire stadium is the atom, the nucleus is just a single cricket ball sitting right in the center of the pitch. That's how incredibly small and dense the nucleus is.
So Rutherford says, okay, cool, the nucleus is in the center and the electrons are just orbiting around it like planets around the sun. But wait,
We have a massive stability crisis here. According to Maxwell's electromagnetic theory, which was very well established, any charged particle that accelerates, like an electron moving in a circle, absolutely must radiate energy. So if it's constantly losing energy by radiating it away, the electron should start spiraling inwards faster and faster until it crashes right into the nucleus. Atom completely destroyed. But atom to stable hote hai na? We exist. So Rutherford's planetary model had a fatal flaw.
We'll get back to that crisis in a second, but first, Section 3, Atomic Numbers and Isotopes. Let's quickly nail down the mathematical rules.
Before we solve Rutherford's little crashing problem, let's take a quick time out to establish exactly how we identify these elements mathematically. It's really all about counting. Your atomic number, represented by the letter Z, is simply the number of protons in the nucleus. Think of this as the atom's identity card. Carbon is carbon strictly because it has 6 protons, period. Then we have the mass number, A, which is the total weight. That's the sum of protons plus neutrons. So Z equals protons, A equals Z plus N. Very simple, straightforward math, students.
Now, please pay attention here, because this is where literally everyone gets confused in the exams. Isotopes versus isobars. Isotopes are atoms of the exact same element, meaning they have the exact same atomic number, Z, but they have different mass numbers, A, like hydrogen 1, hydrogen 2, hydrogen 3. Same identity, different weight. Got it? Isobars are the exact opposite. They are entirely different elements, so a completely different Z, but they just so happen to have the same total mass A, like argon 40 and calcium 40. Yaad rakhna isko, it's a guaranteed exam question.
All right, Chapter 4, Light, Waves, and Quanta. Time to dig into the true nature of radiation. Okay, math break is over. Let's get back to rescuing the atom. To fix Rutherford's crashing electron problem, scientists actually had to stop looking at the atom and start looking up at light. James Maxwell had already told us that light behaves as an electromagnetic wave. Think about the basic anatomy of a wave for a second. You have your wavelength, denoted by the Greek letter lambda, which is just the physical distance between two crests of the wave. And you have frequency, nu, which is how many of those waves pass a specific point every single second. Naturally, a shorter wavelength means a higher frequency. This was the pure classical view. Light is just a continuous, flowing wave of energy.
But here's the catch. Classical physics couldn't explain everything they were seeing in the lab. Enter Max Planck. Planck essentially drops a bombshell on the scientific community called quantum theory. He said, actually no, energy doesn't flow continuously like a river. It comes in discrete, little individual packets. He called these packets quanta, and when we talk about light specifically, we call these packets photons. Imagine paying for something not by swiping a credit card where the money flows continuously, but by handing over exact physical 1 rupee coins. That's what quanta is. And to actually calculate the energy of one of these specific packets, Planck gave us this absolutely magical number, Planck's constant, H, 6.626 times 10 to the power of -34 joule seconds. I mean, just look at how incredibly tiny that number is. The energy of a single photon is simply E equals H times nu. This one tiny number literally bridges the gap between the frequency of a wave and the energy of a particle. It was a total game changer. It changed physics forever.
Which brings us to Chapter 5, the photoelectric effect, the ultimate proof of the particle nature of light.
So, the big debate. Is light a wave, or is it made of these photon particles? We needed solid, undeniable proof. Scientists set up this elegantly simple experiment. They shone a beam of light onto a piece of metal sitting in a vacuum tube. And what happened? Electrons were instantly kicked out of the metal. Instantaneously. I mean, absolute zero time lag. Think about it. If light was just a gentle, continuous wave washing over the metal, it should take some time for the energy to build up before an electron finally pops off. But it happened the absolute millisecond the light hit. Why?
Because light is acting exactly like particles. It's like photons are playing billiards with the electrons. Let's walk through the steps of the photoelectric effect. 1. A photon strikes the metal surface. 2. That photon must meet a strict minimum energy requirement called the threshold frequency. If the light's frequency is too low, you can shine the absolute brightest spotlight on that metal all day long and nothing will happen. 3. If the frequency is right, boom, electrons eject instantly. One photon knocks out exactly one electron. 4. Any leftover energy from that photon? That simply becomes the kinetic energy of the flying electron.
And who put all the math together for this phenomenon? Albert Einstein himself. He used Planck's quantum theory and wrote out this perfectly elegant equation. The total energy of the incoming photon, which is h nu, equals the work function, meaning the exact amount of energy needed just to break the electron free from the metal, plus the kinetic energy of the moving electron. Energy going in equals the energy used plus the energy left over. Perfect conservation. This absolutely undeniably proved that light has a particle nature.
So we've uncovered something absolutely mind-bending today, class. Light, which for centuries we thought was purely a wave, actually behaves as a particle too. This wave-particle duality is the beating heart of quantum mechanics. But here is the real cliffhanger for you to think about before our next class. If something as light and airy as light can act like a solid particle, what does this mean for the physical electrons inside the atom? Could these tiny particles actually be acting like waves? And will this bizarre twist finally solve Rutherford's crashing atom problem? Think about it, guys. I'll see you in the next lesson where we'll unpack Bohr's model. But hi, Carterejo, and stay curious.